Hi, I'm Debra, and I'm so sorry not to be able to be in Havana today. And I will talk a little bit about nuclear physics, gravitational waves, and dark matter as tools to probe neutron stars. These works have been developed at the Federal University of Santa Catarina, and the university is in a wonderful island called Florianopolis. You are all invited to join our group if you like our subject. So I will first show some slides on the evolution of stars. So if you look at the first stages, you can see that there are three choices. The star can be a star which is not very massive, like our sun. So we call it type 1 if the mass range lies in between 0 and 8 solar masses, and then type 2 from 8 up to 25 more or less. And if it's a very, very massive star, then we call it type 3. So the beginning of the evolution is more or less the same, but they all end up in different scenarios. Type 1 stars, like our sun, will end up as a white dwarf. And type 2 and 3 will go through a supernova explosion, and they will become either a neutron star, which is the subject of this talk, or a black hole. So the first neutron star was discovered some years ago by Jocelyn Bell, the beautiful girl you can see in the picture, as a pulsar. So there was a very stable signal that was detected in radio frequency. And believe it or not, some people thought that there were some people from outside Earth trying to connect Earthlings. But this was not the case. It was actually the detection of a neutron star. The main manifestation is then as a pulsar, and it's powered by rotation energy, and many of them have already been observed, all of them in radio frequency. There are other possible manifestations like accreting X-ray binaries. So there is really a binary system, and they are powered by gravitational energy with rotational periods that vary a lot. And then there are other kinds of manifestations which are not very relevant at the moment, but what all of them have in common is that they are very, very dense objects. So the masses are about 1.4 to 2 solar masses, and the radii of the stars are something like 10, 12, 13 kilometers, which makes these compact objects very, very compact, so very, very dense. In 2017, this telescope called NICER was launched, and in 2021 we started getting data from neutron stars sent by NICER. I'm going to talk about them soon. So this paper is about this bizarre state of matter that may exist inside large neutron stars. So the idea is that the neutron star can bear an outside region where the main composition are hadrons, and then a quark core where the confined matter can be found. So the idea is that strongly interacting matter can exhibit the confined behavior in massive neutron stars. So this is not something this is not something unexpected, since if you look at this QCD phase transition, you can see that at the region of neutron stars, so quite high baryonic densities, there is this transition from hadronic matter to quark matter. And then if neutron stars are somewhere in here, they can be composed either of hadrons only or quarks only, or maybe these objects can be hybrids. That's what the paper was telling us about. So actually the idea of hybrid and quark stars is not new. The first suggestion was made in 1969 by Ivanenko and Kurdgelaidze. And then in 1970, Ito proposed the existence of quark stars only, the confined quark stars. And then soon afterwards, Bodmer and Witten proposed a conjecture that would say that the most stable matter would actually be strange matter, which is composed of U, D, and S quarks. Hybrid stars can be either very simple with a quark core and a hadronic outer phase, or it can be more complicated with a quark core, a mixed phase, and then hadrons at the end. I'm not going to talk about the crust. They also may have a crust, but this is a subject for another talk. So these interferometers were built in the United States, like the LIGO, in two places, Hanford in Washington and Livingston, close to Louisiana. And then there was another interferometer called Virgo in Santo Stefano a Macerata, near Pisa, in Italy. And there is also Kagra in Hida, in Japan. The first two, there was this collaboration, LIGO and Virgo. They started detecting gravitational waves in 2015. But the first gravitational wave that was that came from the merging of two neutron stars was detected in 2017. And this was really a unique event. It was so interesting that it was the front page of the Science magazine, like the breakthrough of the year. So if you look at this picture, you can see that it was detected not only in gravitational waves, but also as gamma ray, X-ray, ultraviolet, optical, infrared, radio, and so on. So actually, this neutron star merger, GW170817, because it was detected on the 17th of August of 2017, came from a galaxy far, far away, 140 million light years away, and was observed electromagnetically by 70 observatories all over the world and also in space, plus the LIGO-Virgo collaboration. And what we actually saw was this gravitational wave shapes during the merger. So what our models and simulations show is that there is this in spiral. So two neutron stars are orbiting around each other, and then they come closer, 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 and closer until they merge. When they merge, they send us gravitational waves that we can detect it. So we cannot detect what comes after the merger, like this post-merger event, but probably it will be detected soon. So what do we know about this detection? Then we can analyze tides. And actually, the modeling of tides, like the tides we have in our seas, began in 1909 with Newtonian gravitational by a guy called Augustus Love. So the Love numbers are important, and I'm going to talk about them soon. So they characterized the deformability of a compact object due to an external fields or the external object that generates these tides. 100 years afterwards, Damour, Nagar, Millington, and Poisson extended this calculation to include general relativity effects. And when they do this calculation, one important number is the second order Love number, which is related to a quadrupole formation. So if we look at the Love number for us, it's about 0.3, and for this neutron star merger in gravitational wave GW170817, it's 0.1. So if you want to look at the equations, they are not complicated to follow. You can look at this paper, and you find the derivation of the calculations. So again, the same kind of picture. So we have this binary system, then it comes to in spiral, it merges, and then once we have this the second order Love number, we can also calculate the tidal polarizability, which is given by this lambda factor. If you look at this expression, you can see that this tidal polarizability depends on K2, which is the second order Love number, on C, which is the relation between mass and radius that tells us how compact this object is or how dense it is. And then G is the gravitational constant, radius, and mass. So how do we compute radius, mass, and the compactness? We need to use an equation of state, and we normally use nuclear physics and relativistic models to do so. I will come back to this point soon, but before that I would like to show you the pulsar mass measurements detected so far. It's very difficult to follow these lines with your eyes, but you can see that there is a histogram here, and you can see that most of them are around 1.4 solar masses. That's why many people call those stars canonical stars, the most common ones. So what are the most common constraints that we have, or the most important detected constraints detected lately, so that we can tune our equation of states to describe the astrophysical objects? So you see that PSR, all of them, they are pulsars and different pulsars, and some are canonical with masses around 1.4, like 1.34, 1.418, and some are massive objects like this guy, and this with more than 2 solar masses, and so on. And also we have these constraints coming from gravitational waves. So this is the guy I've told you about soon, and this is another gravitational wave detected in 2019 with, and they both gave us tidal polarizability so that we can use as constraints. So what we see, what we have in common with these 2 important pulsars whose signals mass and radius were sent us by NICER, is that although they have the very different masses, one is around 1.4, so those are the results of 2 groups that analyzed the data, and then this is the other object, and you can see that all radii are about 12 point something, 13 kilometers. Okay, but science never stops. So this is written in Portuguese, but it says that maybe when a compact object is very dense and very compact, it can be constituted of strange matter only. That's what I told you about in the beginning of my talk. And then this strangely light neutron star within a supernova remnant called HESS has a mass of 0.77 solar masses, so less than 1 solar mass, and a radius of the order of 10 kilometers. So maybe this guy has a different nature, and it's composed of deconfined quarks only. More recently, in 2024, this XTE, which is a kind of transient neutron star, was detected with this 1.21 solar mass, so a little bit higher than the mass of our sun, and a very tiny radius of 7 kilometers. So how do we include all this in one simple, not so simple calculation? So actually we start from microscopic physics that involve quantum mechanics, nuclear physics, statistical mechanics, and then we want to go from this microphysics to macroscopic properties. That's the ones I'm telling you about, which are these astronomical observations and the observations coming from gravitational waves. So we compute an equation of state. I'm not going to show the expression. It can be a bit scary. When we use relativistic models, we normally start from a Lagrangian density that has baryons interacting through specific mesonic fields. And once we have an equation of state, we can have, well, once we have the Lagrangian density, we can obtain the equation of state, which is actually energy density, pressure, and baryonic density. And those, this information is used as input to a hydrostatic equilibrium equation, normally called TOV or TOV, from Tolman, Oppenheimer, Volkoff. Oppenheimer is the Oppenheimer. If you haven't seen the film about him, I suggest you do. It's very interesting. And then when we compute all those things, we have as a result mass and radius, and then we can confront these calculations with astrophysical observations. If they are good, if they are satisfied, then we are very happy with our equation of states. If they are not good enough, we have to go back and tune the equation of state, include other ingredients, analyze what was done to have a better equation of state to describe all the data. The question is, can we actually describe all these data that have been sent to us since the beginning of the pandemics, 2020, 2021? And the answer is yes, partially. So we have equation of states that can describe at least some of the astrophysical components, astrophysical observations. And I'm going to show you an example. So on the left, you can see the picture of an equation of state for a hybrid object. So if you look, you have hadronic matter until something flat. That's when there is this discontinuity from the quark core to the hadron phase, and then there is this quark phase. Okay, so these lines, all of them, represent a different equation of states. I'm not going to enter into detail. I'm not just going to say that for hadronic matter, in this case, we have used a model usually called as Valeska model or Bodmer model. And for the quark phase, we have a kind of sophisticated MIT bag model with a vector interaction to make the equation of state a little bit steeper. So once we have the equation of state and we insert the information on the TOV equations, we have what you can see in these graphs, mass times radii. And then you see that we have different results for the different equation of states. And many of them do satisfy these very massive stars. And then if we look at 1.4, which is not shown in this graph, they also satisfy these canonical stars, astrophysical observational constraints that we have used as constraints. So in this case, we are quite happy, but I'm not showing here. This equation of states do not satisfy, for instance, HESS results. And we do not have any equation of state that actually it seems that there is someone that has already managed to satisfy HESS and XT results, but this is quite hard. But the idea is that we can use microphysics, nuclear physics, thermodynamics, quantum mechanics to obtain observational results, which is indeed extraordinary. So what's the future? So I've already told you about NICER. We expect Athena to be launched in 2030, which is another kind of telescope that's going to give us more information on neutron star, or more sophisticated information on neutron star. This evolved laser interferometer space antenna, normally called ELISA, is expected to be launched and to be operational in 2034. And we also have things on Earth. This is something really amazing that Chinese have made that's called FAST, which is this 500 aperture spherical telescope. So if you look at this telescope, it was actually built within mountains. So there are the peaks of the mountains, and there are mirrors everywhere to detect information from space. So what FAST is expected to do is to detect neutron hydrogen to the edge of the universe, to reconstruct the image of the early universe, to discover and detect more pulsars, establishing this timing array, which is important to tune the equation of states, and then to join the international very long baseline interferometry network to obtain hyperfine structures to different celestial bodies, to perform high-resolution radio spectral survey and detect weak space signals, and finally, to participate in the search for extraterrestrial intelligence that you see at the beginning. I started telling you about this little leaflet about this green whatever, but they do expect to find some kind of information from space. And then there is concerning gravitational waves, and there is this telescope called Einstein telescope, which is also expected to be ready and operational by 2030, which is an underground structure. and it's called the third generation of gravitational wave observatory. And with LIGO, Virgo, and Kagra, this cosmic explorer, which is also next generation gravitational wave observatory, is expected to be operational in 2035. So the future is indeed very promising, and many other things can be done so that we can relate nuclear physics to what we see in the universe. So that's it for today, and I hope you enjoyed the talk, and we can talk more about the specifics on the nuclear physics modeling at some time. And I'll also include a link to a channel where there are many videos, unfortunately in Portuguese, but maybe people from Cuba managed to follow on how to build this equation of states. So, gracias, hasta luego, mucho gusto estar aquí. Bye.